So in this section, we're going to discuss how to solve differential equations using the primary tool that we just discussed in the previous one, that is using eigenvalues and eigenvectors. Okay, so let's talk about what systems, first order in particular, systems are, okay, and write them in matrix form. Develop a solution method and solve first order two by two homogeneous, for now, just homogeneous systems of linear equations. Okay. Okay, guys, so what's the structure of a system of differential equations? So you may have like two or even more variables changing on some system at the same time with respect a variable. Let's say typically it's the variable t. Typically these equations are with respect to time, right? We're describing changes with respect to time. Now, what do we have? Some coefficient, some number times the first variable plus another coefficient times the second variable plus dot 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 n variables plus some function here, all right? And then our second equation, I mean, that's the rate of change of the second variable with respect time, which is another linear equation. I mean, some of these coefficients may possibly be even zero. So that reduces systems very, very nicely, you know? So, and the variables are x1, x2, x3, or x, y, z if we want to follow an algebraic, I mean, an alphabetic order, even that's just notation, you know? All right. However, that system right here looks pretty big, looks really big. There has to be a more compact way to rewrite this well, because again, these are going to later be vectors, column vectors, more in particular. Now, what about these functions right here, f1, f2, f3 of t, that are not multiplying any x's or any of the x's, x1, x2, x3, or the variables x, y, or z? All right. Well, whenever we have that extra terms, we say that the system is non-homogeneous. All right, for which, well, those are a nightmare to solve, right? Just like remember undetermined coefficients and variation of parameters. Okay, well, those are actually methods used to solve this kind of system, variation of parameters. Now, imagine doing all this with multiple with multiple variables. Well, the problem becomes pretty interesting to do. However, if we use a Laplace transform, well, that's a whole different story. That may help us do this quicker. But well, we'll see about that later. So now, that means this X bold case, notice the bold case notation. That's because these are matrices, which are sets of vectors. So a matrix equals the product between the two matrices plus another matrix, where in this case, this x prime is the derivative of all the variables involved in the system, the coefficient matrix A, which you guys are already familiar with, and those coefficients could be numbers or functions of t. And then, well, the variables that change x, y, and z, or x1, x2, x3, x4, etc., plus the non-homogeneous term, like that forcing function we talked about back then. All right. So, as examples, just to get started, well, let's write these given systems of equations in matrix form. Okay, so I'm going to leave the general form of a system of equations here at the top, so that's going to help us rewrite the system. So all derivative terms are going to go in a matrix, in a column matrix. That is, let me call this x1, x1 prime, x2 prime. Okay, that's the vector equal to, okay, the numbers that multiply x1 and x2, x1 and x2, those are going to go in a 2 by 2 matrix, 3, 2, 2, -3. And I'm going to multiply this by the vector x1, x2, right? Which are the variables, the variables that are changing with respect time in this case, because it's dt. All right. Okay, well, what about letter B? Well, for letter B, we have a lot going on. First of all, well, dx1 dt, dx2 dt, that also means x prime 1, x2 prime. And that equals, okay, be careful with the coefficients of x1 and x2. Actually, let me highlight them just to help you. Okay, 3t. In this case, the coefficients are not only constants, there are also variables involved. There's a 2 only, there's another 2, and then a negative 3 cosine t. All right, we include the signs. And then we also have other terms that are not multiplied by any variables. Those are the non-homogeneous terms, all right? So that's what makes the system non-homogeneous. So that means coefficient matrix 3t, 2, 2, negative 3 cosine t times x1, x2 plus e to the t ln of t. And that is how we write this system of equations in matrix form. Okay. Now the question here is, how do we solve the system using the tool we just finished discussing? Well, so that's going to be on the next page. So on the next page, let's develop the solution. Okay, the method of solution. Okay, guys. Well, for the sake of simplicity, let's for now limit to homogeneous system. That is a matrix of the form x prime equals to ax. Notice in this case we don't have the other the plus big F. You know, we don't have this term. What makes it non-homogeneous? Because that's we want to do that for simplicity. Okay. So okay, what if in this okay, here's the thing. The derivative term on the left-hand side of the system of differential equations happens to be a matrix of size have about two rows and one column. Well, in this case it doesn't say how many. Let's call it this is an n by 1, all right? It's just a vector column. That means it has n rows, depending on how many equations we have, but only one column. What about matrix A? Well, matrix A will be a square matrix. What size? N by n. What about, what about X? Well, that X describes the 2, 3, 5, 7, 15, 900 million and 13 variables, as many as you want. So that has to be an n by 1 matrix, all right? What happens if you multiply these two matrix? Well, these two must match, and we have a match in here, and the result will be an n by 1, which is what we have on the left-hand side, right? I mean, what I'm doing here, I'm just checking for the consistency of the system before getting into the development of the solution. Okay, guys, what if n equals to 1? What is a 1 by 1 matrix? Isn't that like a number like the number 1, the number 5, the function e to the x plus 4 sine of 3x? Isn't that a 1 by 1 matrix? That's basically a 1 by 1 matrix. Well, that actually tells us simply x prime equals to ax. And guys, that equation can be easily solved using separation of variables, isn't it? Remember the solution to this? That's dx dt equals to ax. That means dx over x equals to a dt. I'm not going to do all the steps, but I mean, that's ln and then do exponentiate on both sides. The general solution to this is x of t equals to some constant c, oh, come on, c e to the at. Remember that basic solution from, what was that, week 1 of class, I guess? Yeah. All right. Okay, but I mean, what happens if n is not equal to 1? How do we generalize this to not a 1 by 1 dimension, but a 2 by 2 dimension, 3 by 3, 4 by 4, 597 million and 84, you know? Yes, we can do that. Do we want to do anything that big? Well, maybe not. All right. Okay, guys. So define the following. Okay. So if this solution works for this equation, that means, okay, let me, okay, guys, to distinguish x being a constant from a vector, I'm going to put like a bar at the top and at the bottom. It's going to look like an hourglass. All right. So that's the notation for vector with for uppercase x. And this will be some constant k. That c, I'm going to replace it with a vector k e to the rt. Okay. Well, actually, you know what? No, let me already get ahead of the game. Instead of using the letter R, let me use lambda, just so you can see where are we going. Well, where is lambda coming from? What is lambda from before? Eigenvalues, right? Okay, so somehow we're going to spawn the eigenvalue, eigenvector equation, and boom, connect with what we're trying to solve. You'll see. Okay, so let's also take the derivative of this. Call this x prime equals to the derivative, that's lambda k vector e to the lambda t. All right. Now, substitute with with x prime equals to a x. Okay. Whoops. All right. So substitute lambda k as a vector e to the lambda t equals to k e to the lambda t, right? I mean, what do we do from here? I would like to simplify this equation because it seems like, oh wait, this is k right here is a vector, isn't it? I would like to divide both sides by eh, the exponential. Well, why can I divide both sides by the exponential e to the lambda t? Well, because it's safe to do so. In this case, okay, by the properties of exponential functions, the exponential is never zero, is it? I mean, unless you have some shifting or something, but in this case, it's not, it's never zero, so that's why I can divide both sides by the exponential. That's going to leave me with x, ah, with the following here, with lambda k equals to some AK. Now the question here is, why didn't I divide both sides by AK? Because there's no division of vectors, right? We can't divide vectors. All right, I'm going to do a little bit of algebra here. Okay, again, guys, that looks like a very simple linear equation from like algebra 1 in high school, but this is actually a fancy equation. This is a vector equation. Be careful. So that means I'm going to leave one side equal to 0. I'm going to move the lambda k to the right-hand side, but I'm actually going to reverse the order of the terms. So that means a k minus lambda k, all right, equals the 0. You guys agree with this? No, the 0 vector, because this is a vector equation, not a scalar equation. Okay, careful again. All right, guys. Well, so guys, here's the thing. If I can't just add. Okay, let me actually factor out k. So a minus lambda times the vector k equals a 0 vector. But we have a little problem, guys, with the quantity inside parentheses. A is a square matrix, isn't it? And lambda is just a constant, isn't it? So we have a disagreement with the sizes. We have a disagreement with the dimensions. I cannot subtract a one by one matrix, which is lambda, from an n by n matrix. What's the trick to make it work? Well, multiply that lambda by 1. What's the number 1 in matrices? What's the unit in the matrix system? What is it? The identity matrix, right? So A minus lambda I times K equals the 0 vector. And guys, that is, doesn't that look like the eigenvector equation? That's all we're gonna do. That's it. I mean, guys, from a basic separation of variables to eigenvector equation, what the hell went on here, right? It's crazy how we do this jump, isn't it? Okay, what does that mean? So, okay, we're not done yet. So, x equals to k e to the lambda t right here, where lambda, you know what it is, right? Is the eigenvalue or a, and k, vector k, is the corresponding eigenvector. That's all it is. Everything just reduces to solving an eigenvalue, eigenvector problem. That means you guys are ready for this. Okay. Well, just a little more information. I mean, like more like technicalities of all this. Okay. So again, superposition. Remember the principle of superposition? So, for instance, if we have some system, the solution will be some constant times x1 plus c1, x1, c2, x2 plus dot dot dot, depending on the order of I mean, depending on the number of equations, depending on the size of the matrix. Again, remember when we first discussed this second order differential equation, the superposition principle. This is a solution separately, this is another separately, or the two are solutions times a constant, right? And what else? A fundamental set of solutions. So X would be a matrix of column vectors x1, x2, x3, dot, 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 xn, which comprises the solution to the system. That's all it is. Remember the Wronskian? These solutions, these column vectors are said to be linearly independent if we find the determinant of this and it's not equal to zero. You guys might remember all of this from 1.5 ago or so, or 2 months or so. So now, what is that? What's everything going to reduce to? Number one, find the eigenvalues and eigenvectors of the matrix, form our fundamental set of solutions, x sub n of t, which is k sub n, the eigenvectors e to the lambda, and there's supposed to be a t here, all right? Yeah, there's supposed to be a t there. Don't forget to write it down. Okay, guys, well, that being said, how about we go over a couple of exercises? Hopefully, I don't know how far we're going to get today, but well, let's see. Okay, solving 2 by 2 systems, which for now, that's what we're going to do. If we have time, maybe we do 3 by 3, all right? But 2 by 2 is more than enough. Okay, guys, well, case one, distinct eigenvalues, where the n by n matrix possess n distinct real eigenvalues. I mean, even though we're doing only 2 by 2 systems, I still want to give you the generalized definition, all right, for a 3 by 3, 4 by 4, million by million, etc. Okay, so then a set of n linearly independent eigenvectors, call them k1, k2, k sub n, etc., can always be found. And well, what is this? X1, the first solution will be the eigenvalue k1 e to the corresponding eigenvector lambda 1 comma x2 equals eigenvector 2 e to the eigenvalue 2t dot dot dot, etc. And that's going to form a fundamental set of solutions to the system on the interval negative infinity to positive infinity. Why is this? That's because of the domain of the exponential function, which is all all real numbers. Okay, the theorem to describe this idea. How do we connect this? Well, let lambda equal lambda 1, lambda 2, dot, 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 lambda n be n distinct real eigenvalues of the coefficient matrix A. of the homogeneous system x prime equals to ax, and let k1, k2, kn, etc. be the corresponding eigenvectors. Then the general solution is given by simply superposition of these two fundamental set of solutions. Okay. However, what do we do? Remember the C1, C2, C3, C4, etc., which are the arbitrary constants to be found how given an initial condition, you know? So we'll see about that. All right, guys. So how about we do one example? Solve the system dx dt equals to 2x plus 3y and dy dt equals to 2x plus y. First of all, write the system in matrix form. That is x prime, y prime, that's the vector on the left, equal to 2, 3, 2, 1. Okay, that times x, y. Or you can do x1 and x2. It doesn't matter. I think I like x and y better, but it doesn't matter. Okay. So number one, find the eigenvalues and eigenvectors. So a minus lambda I, that is 2 minus lambda, 1 minus lambda, 3 and 2 remain the same. Okay, find the determinant of this matrix, 2 minus lambda, 1 minus lambda, 3 and 2. And let that be equal to 0. And you guys know how to solve this problem, right? Well, let me do the whole thing. I mean, we're still going to see this, okay? This is equal to, what is that? Uh, 2 minus lambda times 1 minus lambda minus 3 times 2, which is 6, equal to 0. Let me continue here to get the characteristic equation or characteristic polynomial either way. 2 times 1 equals to 2. 2 times negative lambda minus 2 lambda. Negative lambda times 1, that's minus lambda, and lambda squared, minus 6. Okay, the problem, basic algebra. Combine like terms, solve the polynomial equation, that is lambda squared minus 3 lambda minus 4. All right? Hmm. Factors of negative 4 that add up to negative 3, what are they? Negative 4 and 1. I like that. Negative 4 and 1. That means lambda equals to 4. Lambda equals to negative 1. Forget the 0 here. Okay. All right. Well, let's find the corresponding eigenvectors for these eigenvalues. Here we go. Let's go for the first one. That is, for lambda equals to 4, that is a minus 4 lambda times, well, when we solve the eigenvalue eigenvector problem, we multiply this by some vector v, right? In this case, for systems of equations, we're going to go and use uppercase K, okay? And let that be equal to the 0 vector. All right. What do we do? Okay, let's write the system. Okay, this becomes, what is that? 2 minus 4. And what is that? 1 minus 4. And then, what is this? 2 and 3. Is it okay if I go straight to augmented matrix form? Or do you want me to write the matrices the way I did it before? Is it fine? Augmented matrix? Okay. I mean, we have done a few of this before, right? Okay, so let's just subtract 2 minus 4. So that's equal to, or no, not equal to, this becomes negative 2, 3, 0, and 2, negative 3, 0. Guys, did you see these rows are essentially the same, just opposite in sign? If we were to reduce this matrix, that's going to give us a row of all zeros, the second one. So don't waste your time. Just grab any of your of your rows, whichever you want. Doesn't matter which one. In this case, I would like to take the second one because I don't know. Doesn't matter, really. So this means, okay, decoding this row into an equation that means to be careful. K1, right? This is K, not V anymore. Minus 3K2. That equals to 0. In this case, we will have to solve for any. Okay, I'm going to solve for K1. So 2K1 equals to 3K2. That means K1 equals to 3 halves K2. Okay, guys. The next step, that's the step where we give, in this case, K2, any number. That is, let K2 equals to, okay, guys. Remember how in previous exercises in the previous section, we just gave the number one because that was the number that works? I mean, if you want to do that, that's fine. Just know that 1 times 3 halves is going to give you a fraction. In this case, try to give it a number that actually doesn't give you any fractions, like, how about 2? Okay, so that is K1 equals to 3 halves 2. That equals 3. So the eigenvector k will be k1, k2 equals to 3 and 2. Again, guys, if you want to keep it in fractions, it doesn't matter because, again, these eigenvalues, what do they do? Just stretch the magnitude of a vector, stretch or compress a vector, but they don't change the direction. If the direction were jeopardized, well, then you wouldn't do that. But in this case, it doesn't affect the direction. We can multiply by any number. You can say 2 equals to a million. A million over 2, that's 500,000 times 3, that's a million and a half, right? If you want to do the million and a half, go for it. It doesn't matter. That's a valid solution. Okay. What about for lambda equals to 4? No, not lambda equals to 4. Lambda equals to -1. So you might want to use the back side of the page for this. Okay. Unless you have more space. So for lambda, here I'm just adding another page in my notes. So for lambda equals to -1, that equals, okay, that's a minus -1 times I. Uh, that is essentially a plus I, a equal to the 0 vector. All right, so let's write this as a system. That is 2 plus 1 and 1 plus 1. The other two components, 1, 2, which is 3, and 2, 1, which is 2, they remain the same. And I'm going to go again all the way straight to an augmented matrix. Okay, so let me simplify this system of equations. 2 plus 1 is that equal to 3, and then 0. 2, 1 plus 1 equals to 2, 0. Come on. Do you guys see how these two rows are multiples of each other? We can divide the first row by 3, we can divide the second row by 2, and we're going to have exactly the same row vector on both our rows, you know? So simply, I'm going to take, I don't know, I feel like taking this time the first row, or maybe you want to take the second, doesn't matter. It's the same. Okay. So that means, what is this? 3K1 plus 3K2 equals to 0. All right. So that means I'm going to solve for K1 again. 3K1 equals to negative 3K2. That is, K1 equals to negative K2. So let's let K2, what number would you like for K2 this time? 1? 1 is going to work, okay? This time 1 works. I mean, in the other case, 1 work, provided just keep in mind that you're going to get uh, fractions, but it doesn't matter. Okay, so K1 equals to -1, okay? So our eigenvector for lambda equals -1 will be with components, another K1 and K2. That is, what is that? Negative 1, 1. And we're essentially done with the solution to the problem. Now let's put everything together. Let's write our general solution. Okay. General solution. Our general solution will be of the form x equals to C1 K1 e to the lambda 1 t plus C2 K2 e to the lambda 2 times t. So that's the form of our the solution to the system. And I think we already have everything, don't we? So x equals to C1, whatever that is. Doesn't matter. We don't care for now. What's K1? K1, didn't we get 3, 2? Let me actually lambda e to the lambda 1, which is e to the 4t times 3, 2 plus C2 e to the negative t times negative 1, 1. All right? And guys, that's the result in vector form. Okay? Let me do a little bit of extra work just to show you different ways you may see this. Okay. So I'm going to multiply C1 e to the 4t times 3 and times 2 to come up with another column vector. That is C1 e to the 4t times 3 and 2 times C1 e to the 4t. That's one matrix, really one vector, a column vector plus C2 e to the negative t, but actually times the negative 1 makes it a negative in the front here. And this one simply times 1, C2 e to the negative t, okay? And then how about we add these two matrices? These two 2 by 1 matrices, two column vectors essentially. I mean, vector addition from calculus 3. X component with X component, Y component with Y component, right? I mean, it's just that this time we have fancy components. So that is uh, 3C1 e to the 4t plus, or rather minus, C2 e to the negative t, 2C1 e to the 4t plus C2. Actually, I'm going to replace this big X into X and Y instead, which is really what we wanted to find, isn't it? Now, if you don't like this is still a vector. If you don't like this vector form, if you want, okay, write it in as a set of equations. X equals to all this 3C1 e to the 4t minus C2 e to the negative t. Y equals to 2C1 e to the 4t plus C2 e to the negative t. And put curly braces to put this together. Goodness, I wonder if that kind of looks familiar from something you've seen before in the past. And if so, what does that look like? Hmm? Coefficient, what else? Notice the variable t. We have equations in terms of t for x and y. What are they? Calc 3. This is Calc 3, technically, basically, just to give you a hint. Starts with a P. I can think I gave it away with the P. Parametric equations. This is a set of parametric equations, guys. Well, why is this important? Well, that's because when it comes to graphing the solutions, well, essentially the solution to a 2 by 2 system will be a curve in the plane. Well, I can't graph this one because we don't know what C1 and C2 are. However, if we were given an initial condition to find C1 and C2, we can graph them, which is what we may get the chance to do, hopefully right now. Okay. All right, guys, let's have a look at the next example, which is, oh, speaking of the devil, that's actually an initial value problem because now we have x of 0 equals to 0, 5. Okay, let's get started by getting the eigenvalues and eigenvectors. So this means x prime, y prime equals to 1, 2, 3, 2 times, what is that? xy, right? Which is the x prime equals to, oh, come on, what am I doing? Ax, right? That's a homogeneous system we've been describing for the last hour or so. Okay? So, eigenvalues. That is the determinant. Let me go straight to the determinant of 1 minus lambda, 2 minus lambda. The other two elements just remain the same, 3 and 2. And let that be equal to 0. And solve the determinant equation. 1 minus lambda times 2 minus lambda minus 2 times 3, which is 6. Let it be equal to 0. Expand, combine, simplify. 2 times 1 is 2. 1 minus negative 1 times negative lambda minus lambda. Negative lambda times 2 minus 2 lambda. Negative times a negative is positive lambda squared minus 6 equal to 0. Another quadratic polynomial because 2 by 2, right? If we were working on a 3 by 3, cubic polynomial n by n, nth degree polynomial. Lambda squared minus 3 lambda, and what is that? Minus 4? So what about factors of negative 4 that add up to 0? I mean, that add up to negative 3. Negative 1 and 4, okay? Negative 1 and 4. All right. I wonder if this is the same one we did in the previous section. No, I don't think this is the one. No, no, never mind. Never mind. Don't listen to me. Okay. So this means lambda equals to 1 and lambda equals negative 4. So let's get the corresponding eigenvectors for this. Okay. So that is 4.
Professor.
Yes.
Shouldn't it be lambda plus one and lambda minus four?
Um, yes, you're right. Okay. So plus 1 and then minus 4. Yes, because you want the addition to be negative, right? So the largest has to be negative. So that means negative 1 and positive 4. Thank you. Good catch. So let's do this for positive 4 first. Okay. Lambda equals to 4. All right. That'll be lambda equals to 4. That is okay. A minus 4 times the identity matrix times A1, which is the eigenvector related to or corresponding to the eigenvalue of lambda equals to 4 equal to the 0 vector. That means 1 minus 4, 2 minus 4, and then 3 and 2 here. Augmented matrix with a 0 column, the vector on the right. 1 minus 4 and 2 minus 4. Okay, 1 minus 4. That's 3, 2, 0, 3, negative 2, 0. All right. Did I get this right? Oh, this is supposed to be negative, right? Okay, negative 3. Come on, guys. Can you tell that these two rows are multiples of each other? Don't even bother reducing the matrix. Just grab your favorite row. I'm going to grab the second row. Okay. I'm going to grab the second row, and that'll be 3k 1 minus 2k2 equals to 0. And I'm going to solve for k1 because I want to have everything positive, I guess, right? So 3k1 equals to 2k2. This will be k1, all right? This would be k1 Okay, never mind. Yeah. K K1 equals to 2/3 K2. All right. What would be your favorite value for K2 this time? 3. Let K2 equal to 3. K1 equals to 2 divided by 3 times 3, which is 2. What's the eigenvector? A1 would be 3 for K2 and 2 for K1. All right. So far, so good. What about lambda equals to, what is that, -1? So for lambda equal to -1. What is that? So this will be A minus -1 times the identity times K2, which is the second eigenvector. Let that be equal to the 0 vector. Okay, so that means A plus the identity K2 equals 0 vector. But I mean, adding the identity matrix, that means add 1 to the elements along the main diagonal. So that'll be 1 plus 1, 2 plus 1. Along the main diagonal, the other two elements remain the same. And I'm going to go straight to an augmented matrix. So 1 plus 1 equals to 2. This is the same as saying 2, 2, 0, 3, 3, 0. Come on. Aren't these two rows multiples of each other? Just grab your favorite row. Doesn't matter which one. I'm going to get the first one this time because smaller numbers, that's not necessarily easy. They're nice integers, all right? So 2k1 plus 2k2 equal to 0. Solve for k1. 2k1 equals to -2k2 and k1 equals to -k2. That means, wait. Let k2 equals to what works this time? 1? 1. That means k1 equals to -1. So our second eigenvector, k2, will have components -1 and 1. All right? And we have to write our solution. And I'm just going to write the, what's it called, the vector notation because I need to substitute the initial condition. Okay, so general solution, that'll be C1 K1 e to the lambda 1 t plus C2 K2 e to the lambda 2 t. Okay, we have everything we need. This will be x, fancy x, equals to C1. What was K1? Oh, well, first the exponential e to the 4t times the vector 2, 3, right? Plus C2 e to the, what was that? Negative t? Negative t times the eigenvector -1, 1. So that is the general solution. What particular solution? Okay, for a particular solution, let me use the initial condition, the given initial condition, x of 0 equals to 0, 5. This means x of 0 equals to 0 and y of 0 equals to 5, essentially. Again, in both case, x stands for x, y, or x, y, and z, or x, y, and c, and w, have many variables you have. Doesn't matter, okay? So, with x of 0 equals to 0, 5, what are we going to do? X of 0 equals to C1 e to the 4 times 0 to 3 plus C2 e to the -0 times negative 1, 1. Okay, the exponentials raised to the 0 power, don't they go to 1? Which means, oh, but what's x of 0? First of all, this is the vector 0, 5, isn't it? That equals C1, this term goes to 1 times 2/3, I mean not 2/3, 2, 3, plus C2 e to the negative 0, that equals to 1 times the vector negative 1, 1. Okay, guys, what is this? Combine this together, 0, 5. If you want to go to the back side of the page, that's fine. Okay, what is this? C1 times 2 plus, or rather minus, C1, and then the second row, C1 times 3, that's C3. I mean 3C1 plus 1 times C2. This is another by one, no, 2 by 1 matrix, right? So how about this is a system of equations, really? 2C1 minus C2, this is supposed to be a C2. C2, 3C1 plus C2 equal to 0 equals to 5. So that's the system we need to solve to get the constant C1 and C2. Don't even set up a matrix for this one because this can be easily solved by elimination. If we add together the rows, 2C1 plus 3C1, 5C1, these two cancel, equals to 0 plus 5, which is 5, and C1 is 1. To get C2, just substitute C1 into any of the equations. I'm going to do the first equation, 2 times C1, okay? 2 times C1, which is 1, minus C2 equals to 0. That means negative C2 equals to negative 2, and C2 equals to 2. And guys, we have the initial value problem solved. Let's go back and write the particular solution like this. X with a bar equals to e to the 4t times C1, which is 1, plus, or rather times the vector 2, 3, plus C2, which is what? 2, e to the negative t times the vector negative 1, 1. All right? So that is the particular solution. Uh, in today's lecture, I'm not going to have time to graph the solution. I need to actually take my time in getting the entries, the inputs, and all that. I'm going to do that at the beginning of next time. Okay? So let's stop here.